Today's Chem 111 video is about sp2 hybridization. We've already talked about sp3 hybridization in class, and I just want to remind you first of all what hybridization is. So hybridization is a way for us to think about atoms and molecules and think about the kind of orbitals that might overlap to form the bonds in a molecule. Hybridization is something that we as humans made up. It's pretty much a false picture, but it's really useful for us to understand bonding. So I want to keep both those things in mind. It's very useful, but it also describes a situation that doesn't really occur, which is, so for instance, in this molecule here, ethylene, we want to think about the hybridization of this carbon atom, which refers to orbitals, fictional orbitals, on the carbon atom that exist just because the carbon atom knows it's about to form this molecule. All right, so sp2 hybridization. Let's start with sp3. Hybridization comes from knowing the steric number of an atom. So when we talked about sp3 hybridization, we looked at atoms with a steric number of 4. sp3 is the name of that type of hybridization. And there are 4 hybrid orbitals formed for an sp3 hybridized atom. So 4 hybrid orbitals. The number of hybrid orbitals equals the steric number. The number of hybrid orbitals is also shown in the name. So sp3 is made by combining one s and 3 p orbitals, a total of 4 orbitals, gives you 4 hybrid orbitals. sp2 hybridization is for something like a carbon atom in this molecule. This carbon atom has a steric number of 3. Actually, they both do. The hybridization type is sp2, and there will be 3 hybrid orbitals formed. And if you're in a guessing mood, you can figure out what happens at steric number 2, but we'll cover that later. All right, so I want to just talk about the orbitals for a second that are formed. In sp3, if we were talking about something like carbon, we would take the 2s orbital and the 3 2p orbitals, and we would combine them to form 4 sp3 orbitals. So we would combine them to get 4 sp3 hybrids that would be at some different energy. I'm not drawing these on the same energy axis here, but that's what you would have. So for sp2, we're going to do something different. So I'm going to erase this arrow. For sp2, we're going to look at the same atomic orbitals. So the 2s and the 2p, but here we're only going to make 3 hybrid orbitals, like our table says. So we're going to take the s and 2 of the p orbitals and make 3 hybrid orbitals. So from this, we will get 3 sp2 hybrid orbitals, and we have 1 p orbital left over. If we only make 3 hybrid orbitals, we make that out of 3 atomic orbitals. We're not allowed to lose orbitals. And so we still have 1 2p orbital left over. And this is the orbital configuration for sp2 hybridization. So just like the table says, we have 3 hybrid orbitals, and we have 1 p orbital left over, and that p orbital is going to be important in bonding. So now what I want to do is show you spatially what those orbitals look like. So I'm going to erase my ethylene molecule and our table and look at these hybrid orbitals. So the shape of hybrid orbitals we talked about for sp3. The shape of hybrid orbitals is a combination of s and p shapes. Whoops. So they have that sort of 2-lobe structure that p orbitals do, but the lobes are not equal in size. So sp2 orbitals look different than sp3 orbitals. If you think about it, sp3 orbitals are sort of 1/4 s. sp2 orbitals are 1/3 s. I'm not going to worry about the distinctions in how we draw them too much. So an sp2 orbital has the same general shape as an sp3, which is it has a small lobe and then a large lobe like this. So I always think it looks kind of like a Pepperidge Farm goldfish. There we go. So it has two lobes. This lobe here is much smaller, so it's not generally as important in bonding. So very often we will draw it a little simpler. Just draw the big lobe when we're talking about the sp2. So keep in mind it has this other lobe here, but we're going to draw them as sort of this fat teardrop shape. So sp2 hybridization, what does it look like? Well, you know that sp2 hybrid orbitals are for when you have a steric number of 3 or a trigonal planar geometry. The hybrid orbitals line up with that geometry. Just like in sp3, the hybrid orbitals are tetrahedrally organized. So I'm going to first draw this from the side. And what I like to do is actually draw sort of the bond indicators, even though I'm only drawing an atom, because it helps you see the geometry of the orbitals. So trigonal planar, if we were looking from the side, would have one orbital located along this line in the plane of the board, and then it would have one coming out and one coming in to the board. So now I'm going to draw in the orbitals. They look like that. This one coming out and this one coming back into the board a little bit. Okay, and there the angles between them are 120 degrees. We have the leftover p orbital to think about. And that leftover p orbital, you can guess where it goes. It sticks up here and down here. So the leftover p orbital is perpendicular to the floor, coming through the plane of the sp2 orbitals. Okay? I'm going to draw this atom one more time, looking from the top down. So this is a side view right here. And now we're going to draw a top view. So a top view, if I were looking down on my carbon atom, would just have my 3 sp2 orbitals in a nice trigonal planar geometry, like that. Okay, so I'm looking from the top down, so the angle, if I draw the lines here, the angle between any of these is 120 degrees. And in this case, the p orbital is perpendicular to the plane of the sp2 hybrids. It's sticking straight out of the blackboard. So I draw that sort of, or try to draw it as a lobe coming out this way and a lobe coming out in the back. That would be hidden behind my other orbital. All right, so but that orbital's sticking out of the blackboard. All right, that's what the sp2 orbitals look like. Along with the p orbital that goes with them, because remember we have that one leftover p that we didn't mix in to the hybrids. All right, so the last thing to show you then is how these sp2 hybridized atoms come together to form a bond. So now I'm actually going to leave my side view carbon up here and draw another carbon next to it. And what I'm going to do is draw the bonding in ethylene. So I'm going to redraw the Lewis structure up here. Remember, ethylene has a double bond and then 2 bonds to hydrogen up there. Okay? So we have a carbon here. To form ethylene, we bring in another carbon, which is also sp2 hybridized. So this carbon has an sp2 orbital that overlaps with this sp2 orbital. It also has sp2 orbitals sticking into the board and coming out of the board. And it also has a p orbital that, when we draw it this way, is sticking, again, in the plane of the board, up and down through the plane of the sp2 hybrid orbitals. All right, so now the picture's gotten really crowded, but I'm going to show you the important things here. So these 2 overlapping sp2 orbitals, whoa, squeak, form a sigma bond. It looks just like a carbon-carbon single bond. It looks just like a sigma bond that you'd form from sp3 hybrid orbitals. The other bond, there are 2 bonds in this. There is one sigma bond. We could say that's the sigma bond. The second bond that forms with sp2 hybrids, the second bond of a double bond, is something called a pi bond. Okay? And the pi bond has two regions of bonding electron density because it forms from the overlap of the p orbitals. So these two lobes up here overlap, and these two lobes down here overlap. So just like a p orbital has two regions of electron density above and below the atom with a node in the middle, a pi bond that's made from two p orbitals overlapping has electron density above and below the molecule and a node in the middle along the bond axis. And that node is important because that's where the sigma bond sits. So there's already a lot of electron density there. I want to emphasize because a pi bond kind of looks like two bonds, but it's not, it's one. So here is the sigma bond in my picture. And here, both arrows, here and here, this is, I'm going to come over to this side, try not to get caught. This is the pi bond. Both these regions of density are one bond. So my double bond is a sigma bond and a pi bond, like that. Okay, the H's on ethylene, I'm not going to draw those on this picture because it'll just get complicated, but I'll draw one of them. How's that? So an H atom has a 1s orbital. That's all it's got. No opportunities for hybridization. So the H atom, for instance, comes in with its nice spherical s orbital and just forms a nice sigma overlap with one of the remaining hybrid orbitals. All right, the last thing I want to do is show you actually a model, and we'll have a chance to look at these in class. I'm going to set down my microphone and come a little closer, not too close. All right, this is an sp2 hybridized carbon atom. So the black ball is a carbon atom, and it has 3 gray hybrid orbitals, just like that. And then sticking through it is a p orbital. It doesn't really look like a p orbital, but if you imagine these 2 pink balls are the lobes of a p orbital, this is the p orbital that goes through the plane of the hybrid orbitals. And I have another sp2 hybridized carbon atom right here. And I can stick these two things together. In fact, my sigma bond should be a little more symmetric, but I have replaced the wrong bond. So if I overlap them, I get a nice sigma bond here in the middle. And then I just want to show you the overlap with the pi bond. So the p orbitals overlap, and we can show that by sticking some electron density between them. There's half the pi bond, and here is the other half, like that. Okay? So 1 sigma bond, 1 pi bond. And then finally, something this model shows really nicely, because it shows the bonding, is that you can't rotate this molecule. Okay? If I try to rotate it, I can't because the pi bonds are stuck. So if I take that pi bond out, another way to say it is this. If I take that pi bond out and now I rotate the molecule, I say, oh, I'm going to rotate the p orbitals like this, right? So they're perpendicular to each other. I can't do that. It won't form a pi bond, right? So if I rotate them, help, this electron density has no p orbital. The p orbital has to come around, line up with the other p orbital to overlap. All right. So we'll have a chance to play with these models more in class, but there you go. Pi bond, ethylene. And that is sp2 hybridization.